Hello, fellow problem solvers. So today we're going to be doing an inequality from the 2008 IMO, problem number 2. I suggest you try this problem out for a minimum of 30 minutes, ideally an hour and a half to 2 hours, but not more than 3 hours. And if on the other hand you'd like to go along with us, I suggest you give it a go for the next 15 minutes. And now, without further ado, let's begin. So what the problem says is for x, y, z that are real numbers, and all are different than 1, we need to prove this inequality. And that's part A. Part B is to prove that the equality case holds true for infinitely many rational triples. And now with that, what's the first? So the first thing, actually, once I saw B, I was like, you know what, I'm not going to start with Cauchy or something like that. Let me try to, I'll need to find an infinite number of triples somehow. Let me see what this is like. These are all separated. That's like the first thing I noticed. So this is like x over x minus 1. And likewise, and this is like, what? This is x minus 1 plus 1 over x minus 1. So this is 1 plus 1 over x minus 1. And now maybe squares of these. How do I use this? It's not that nice. What happens if our x minus 1 is a, and I just switch this around? I'll have an ugly condition, but what will this turn into? I'll have a plus 1 over a squared. So it's much nicer for me to have just a squared in the denominator than it is to have a minus 1 squared, like in general. So let me just try this out and see what happens. So this turns to be 1 plus what? So this is 1 plus 1 over a squared, so it's 1 plus 2 over a plus 1 over a squared. Cyclically, we need to prove this is greater than or equal to 1 for ABC. And this doesn't seem simple, doesn't seem nice. Maybe there's a different switch we can take. Actually, here I invite you, if you haven't already, played around with some switches, see if there's a nice way for you to deal with this expression. Really, that's my only piece of advice. How would you deal with this expression? It's somewhat ugly. I don't like it. That's the thing, I don't like this expression. But here I would actually invite you to pause and see if maybe the switch actually works. I don't know. I'm going to pause and try to work it out myself, and I invite you to do the same. So here's the next step. So the thing I ran on was let's try to make the inequality look nice and make the condition look ugly. And the condition is somewhat ugly. Like when you make this change, x over x minus 1 is a. Now what the condition looks like is a over a minus 1 times b over b minus 1 times c over c minus 1 is equal to 1. And also x is different from 1. A should then be different from 1. Can that ever be true? No, then x would be x minus 1. So a is different from 1. And yeah, that's just it. A is different from 1. And now we have, this is our condition. This is what we need to prove. And, this is what we need to prove, and this is our condition. And now with that, what is this? This is AB. Let's just multiply. This is ABC. ABC cancels out with ABC. So we will be left with what? A minus 1, B minus 1, C minus 1. So that gives us, A is minus, so it's there's an A plus B plus C. And then AB minus is equal to AB plus BC plus CA. And then the one is a minus. And the minus is on the same, the minus 1 is on the same side as A. And this is what the condition is then. And if this is our condition, can we prove this is the case? Wait a second, this is, should we be able to do this quite quickly for some reason? Let's see, what is this? This is, I'm thinking if I square this, I'm going to get this and a little bit of this. That's the only thing I have right now. It's driving me someplace. I'm not sure. Actually, pause for 5 minutes and see if there's anything you would like to do with this. So the thing I'm getting now is, okay, let me just a squared plus b squared plus c squared greater than or equal to 1. If and only if a plus b plus c squared minus 2ab minus 2bc minus 2ca is greater than or equal to 1. And now with this, minus twice this, minus 2, minus this 2 times. And take the 2 over there, make it a plus 2. And we have this is true if and only if a plus b plus c squared. Then this minus becomes minus 2 a plus b plus c plus 2 greater than or equal to 1. Okay, and now we are a plus b plus c minus 1 squared is greater than or equal to 1. Okay, so this is, and this is true. So part A is done. And now we need to show that an equality holds for infinitely many rational triplets. So we need to show that a plus b plus c is equal to 1. And the condition, which is what? That's ab plus bc plus ca plus 1 is equal to a plus b plus c, which is now equal to 1. So we need to show that both a plus b plus c is 1 and ab plus bc plus ca is equal to 0 for infinitely many rational triplets of abc. Okay, so now let's do this. Well, how are we going to... okay, let's eliminate one of them. Like we have 2 equations, 2 unknowns. Let's eliminate, so this is ab plus c times a plus b is 0, i.e. actually ab is equal to negative c, a plus b. Negative c is equal to a plus b minus 1. And now with that we have ab is equal to what? A plus b minus 1 times a plus b. And this is going to be a plus b squared minus a plus b is equal to ab. And now we'll have a squared plus ab plus b squared minus a minus b is equal to 0. How do we find infinitely many rational triplets for this thing? Okay, here I invite you to pause for 3 minutes and figure that out. And the answer is, it's a quadratic in either a or b. And if it's an a, it's a squared plus a times b minus 1 plus b squared minus b is 0. And now we need to make sure that the discriminant needs to be, I believe, rational. Like the square root of the discriminant is equal to what? This squared, so it's b minus 1 squared minus 4 times this. 4 times b squared minus b. This needs to be a perfect square for infinitely many b. And then if we have this a square, then a will be rational, and then c will be rational because a and b are rational, and c is a plus b minus 1. So now let's solve this. How can we find infinitely many rational b's such that this thing right here is a perfect square? Well, let's see what this is like. This is b. I don't like that there's like minus 4b squared here. So that's minus 3b squared. So it's going to be plus 4b minus 2b gives you plus 2b, and then a plus 1. So this needs to be a square. Okay, that's just beautiful. Like, how am I going to make this a square? And I invite you to think about this for 5 minutes, and here's the next step. And the hint is this. We can actually factor this quite nicely into 3b plus 1 times 1 minus b. And now, to make this a square infinitely many times, it's enough for us to make both of these squares of rational numbers. So now, if this is, say, L squared and this is K squared, then what do we have? What's the relationship? The relationship is K squared minus L squared, where these are rational numbers. So actually what? K squared is going to be 1 minus b. And L squared is going to be 3b plus 1. So 3k squared is 3 times this minus 3b. So 3k squared plus L squared is going to be equal to 4. And these are rational numbers. Now, can we make this true for infinitely many rational numbers k and L? I think if we can make, if k is rational, then actually yes, k needs to be rational. K and L both need to be rational. So this equation has infinitely many solutions in rational numbers. We're done. And okay, now seeing these squares, like one thing I want to do is just like k is 2k prime, L is 2l prime, and we have 3k squared, k prime squared plus L prime squared is equal to 1, once we cancel out the 4. And now this is like sort of reminding me, like here's what I need. I just need, if I have 3x squared plus, I mean we already, capital X, 3x squared plus y squared is z squared. For infinitely many x, y, z, then x over z squared, y over z squared is z squared over z squared, and we have our k and l. So if we have infinitely many integers such that 3x squared is equal plus 3y squared is z squared, then we're done. And I think for this, I'm reminded of Pythagorean triplets. And I mean, this is literally my thought process here, is I'm using stuff I already know to solve this, and I'm testing it out. I actually don't know if this will work or not. So let x be m times n, like that's usually how the Pythagorean triplets look. And then we have z minus y times z plus y is equal to 3m squared n squared. Let's make it like this is 3m squared, this is n squared. What needs to be true? Then we'll have a solution for z is 3m squared plus n squared over 2, and y will be 3m squared minus n squared over 2. And it seems this solves our problem. We just need m and n to be of the same parity. Just to be on the safe side, I would make them odd. Oh, actually, wait. If I have... Oh, here's an important part. We need to find infinitely many solutions which are all relatively prime to each other, such that x, y, z are relatively prime to each other, because, mind you, if, like, what's one solution? I just want to find, let's see, just one solution. So we have 1, 4, 9, these are squareds, and we have 16, 16 minus 4 is 12. Okay, like 4, 4, like 2, 2, 4 is one solution, I believe. And then you can't, actually, so is then, yeah, 1, 1, 2 is a solution. But you can't count them as two separate solutions, because once you divide by z squared, you're going to get the same solution. You're going to get 1 over 2 plus 1 over 2. Yeah, you're going to get k is 1 over 2. K prime is 1 over 2, and L prime is 1 over 2. And you're going to have the same solution. So we need x, y, z to be relatively prime. So to make sure that happens, let's just pick m, n are relatively prime, and let's make them both odd. I mean, they're just like maybe prime numbers, who knows? And then this is an integer, this is an integer, and if a prime divides, say they are odd numbers not divisible by 3, just to be on the super safe side, then this isn't divisible by 3, this is not divisible by 3. If p divides m, then, and c divides x, and then it divides z, then it would be 3 would divide n, if it divides m, it divides n, contradiction because they're relatively prime, and can they divide each other? If a prime divides both this and this, it divides their difference, which is what? The difference is 6m squared, and yeah, I think this is good. This works out. One is going to be, actually, which one is this one going to be then? One is going to be even, I believe. Wait, so this is 1, 1 mod 4, this is 1, okay, this one's odd, this one's even. So yeah, oh, that works. So this is how we can find a solution. Now I invite you to take 10 minutes and write up the whole problem. And here's the write-up. So the first thing we do is set up the switch. We say what the condition becomes, and then we say this is what we need to prove. And this is true if and only if s minus 1, where s is the sum of a plus b plus c, squared is greater than or equal to 0. And now with that, we've proved part A, and we move on to the second part, and we do it like, and we finish up by doing this calculation. And then we say like this holds true, and this gives us a unique x, y, and z. We just need to make sure that none of these will like ever repeat, and like we would need to check that. Alternatively, there's a different way to write it down. To like find a different solution is just like by having the discriminant need to be a square. You can have b is s over t and set t minus s and t 3s plus t as squares. T equals this gives you the squares, which gives you a, b, c, and gives you the corresponding x, y, and z. For different s, these will be different values. So this solves our problem, and as always, thanks for problem solving.